Welcome to the deep dive. Okay, let's unpack this. Today, we're plunging headfirst into the world of network security. Specifically, we're looking at it through the lens of Junos OS and Juniper's SRX devices. And our source material for this deep dive, it's a set of exam practice questions for the JN0-232 certification. Now, don't worry, we're not actually taking an exam here. Our mission is really to pull out the important nuggets of knowledge from these questions. Think of it like a shortcut to understanding some core concepts in network defense, how Juniper systems handle keeping everything secure.
Yeah, what's fascinating, I think, is how these questions, which might seem simple on the surface, actually reveal some really crucial architectural choices and fundamental security principles that protect whole networks. We'll get into the what, but also the why these things are designed this way, what problems they really solve.
Absolutely. We're basically peeking behind the curtain. So whether you're a network pro, maybe aspiring to be a cybersecurity expert, or honestly just curious about how the internet stays safe, you're going to get some aha moments today about controlling and protecting traffic, how it's managed professionally. Let's get started. Build it up piece by piece. Okay, so let's kick things off right at the edge. The very first line of defense. In Junos OS, what's the object that protects a specific zone against common stuff like, say, SYN flood attacks? The answer is screen. But what does that actually mean? Why is it the first line?
Okay, so a screen in Junos, it's basically a dedicated security feature. Think of it like a digital bouncer at the entrance to a security zone. Stateless, mostly. Its main job is protecting that zone from common network attacks. You mentioned SYN floods, that's a classic one. But also things like port scans, ICMP floods. And the really critical point, like you said, is where it works. It's at the ingress point of the traffic. So it applies these predefined protections before the traffic even gets properly into the system to be looked at by, say, security policies.
Ah, okay, so it's like a pre-filter.
Exactly. It drops the obviously bad stuff right at the door. And that saves a lot of processing power, right? Keeps the device stable, lets legitimate traffic through without getting bogged down. It's different from a security policy, which comes later and decides if legitimate-looking traffic is allowed or denied based on rules.
That difference is key, isn't it, between screening out the obvious junk early and then applying policy to the rest. So a screen isn't just a wall. It's more like an intelligent shield checking for known bad patterns right at the door. Pretty efficient. What happens if you don't have a screen configured properly for something like a SYN flood?
Well, that's where you can run into trouble. Without a screen or a badly configured one, those attacks can just hammer the device. They eat up resources, CPU, connection tables, stuff like that. Performance drops, and legitimate users might get denied service. A SYN flood, for instance, could just fill up the session table, making the device unresponsive. So it's defense in depth, but it's also about efficient defense. Stop the bad stuff early.
Makes total sense. Shed the bad traffic as soon as possible. Okay, so moving past that initial screening, once traffic is kind of deemed okay to enter, we still need to manage how it talks between our internal network and the outside world. And that brings us to NAT, right? Network Address Translation. Let's start with SourceNet. What's its main job? Why do we use it so much?
Right. SourceNet or SESNet, its primary function is letting hosts inside your private network, the ones using private IPs like 192.168.something reach the internet. It works by translating those multiple private IP addresses from your internal network into usually one or maybe a few public routable IP addresses when the traffic goes out. And this does two really important things. First, IP conservation. Hugely important, especially with IPv4 running out. SNAT lets tons of internal devices share a small number of public IPs. Second, from a security angle, it hides your internal network structure. Yeah, anyone outside just sees the public IP, not all your internal addresses. It's not foolproof security, but it makes reconnaissance harder for attackers. And usually, when we talk about SNAT in practice, like at home, it's often port address translation, PAT, which uses different source ports so many devices can share even a single public IP.
So my laptop, my phone, the smart TV, when they're all online at home, they're probably using PAT, a kind of SNAT. And to the outside world, they all just look like my one public IP address from my ISP. That's clever, conserves IPs and adds a bit of privacy. Does that translation process itself create any specific security things to watch out for?
Well, the main thing is state management. The firewall has to keep track of all those translations in a session table so return traffic gets back to the right internal device. If that table gets overloaded somehow, maybe through an attack or just extreme load, new connections could fail. But honestly, for most setups, the benefits IP saving, hiding the internal layout, they really outweigh that.
Right, that state table is crucial. Okay, but what about the other way around? We talked about outbound. What if the outside world needs to reach a server inside my network? How do you handle that without just opening the floodgates?
Yeah, good question. That's where destination NAT, or DNAT, comes in. DNAT is specifically for when external users need to connect to an internal server that only have a private IP address. It works by taking the public IP address, and often the specific port that the outside world connects to, and translating it into the server's private IP address and maybe a different port on the inside.
Okay, so if I'm hosting a website from my network.
It's exactly, or an email server, a game server, anything like that. DNAT is essential. Without it, you'd either need to give that server a real public IP, which is usually bad for security and waste IPs, or nobody could reach it from the outside. The big security point with DNAT, though, is that you are intentionally opening a path in, so you absolutely have to protect that path with strong security policies and make sure the server itself is hardened and patched. A common mistake is making the DNAT rule too wide, accidentally exposing more than you intended.
Gotcha. So SNAT for outbound, internal users going out, DNAT for inbound, external users coming into specific services. Two sides of the NAT coin. And that warning about careful configuration with DNAT seems really important. Don't just punch a hole without thinking. Okay, so beyond managing traffic flow with NAT and screens, how does a system like Junos OS actually run all this? Let's get into the hardware and software bits. This is where it gets interesting. In an SRX device, which specific part handles the heavy lifting for security stuff like, say, content filtering, antivirus, web filtering?
That would be the Services Processing Unit, or SPU. This isn't just software. It's a dedicated hardware component, a specialized chip, really. Its whole reason for being is to handle those advanced, often intensive security functions. Things like deep packet inspection for the firewall, IPS, AV scanning, filtering web content, all that demanding stuff.
Dedicated hardware. Why is that necessary?
Well, because those functions are really resource intensive. If the main CPU had to do all that and manage routing and everything else, performance would just tank, especially under heavy load. So the SPU offloads that work. It lets the device maintain high throughput, high speeds, even while applying complex security. It's about making sure security doesn't kill performance. They need to coexist.
Oh, wow. Okay, so a specialized chip just for security tasks.
Yeah.
A real powerhouse. Now let's contrast that. On that same SRX device, which bit is responsible for the routing, the management, the overall control plane?
That's the routing engine, or RE. The RE is, well, it's the brain of the device. It handles all the control plane tasks. And for anyone listening, the control plane is basically the part that makes decisions, figuring out routes, managing the configuration, handling user logins, that sort of thing. It doesn't actually move the data packets itself, but it tells other parts how to move them.
It's the manager, the decision maker.
Precisely. And just to complete the picture, there's usually another key component, the packet forwarding engine, or PFE. If the RE is the brain and the SPU is the security specialist, the PFE is like the raw muscle for moving traffic. It handles the data plane. Its job is just high-speed packet forwarding, taking packets in one interface, figuring out where the RE told it to send them based on the routing table, and blasting them at the correct interface. Speed and efficiency, that's the PFE.
Okay, so what does this all mean for us? We've got this clear separation. RE is the brain making decisions, PFE is the muscle moving packets fast, and SPU is the specialized muscle doing the security heavy lifting. Why is that separation so important, especially for a security device like an SRX?
Oh, it's absolutely fundamental for a few key reasons. One, performance. Like we said, the PFE and SPU can run flat out without being slowed down by the RE thinking about routing updates or config changes. Two, stability. If, say, a routing process crashes on the RE, the PFE can often keep forwarding traffic based on the last good info it had, minimizes disruption. Same if the SPU gets hammered, doesn't necessarily stop the RE from managing the box. And three, security itself. Isolating the control plane, RE, from the data plane, PFE, SPU, reduces the attack surface. An attack hitting the data path doesn't automatically compromise the device's brain. It helps keep the device manageable even under pressure.
That architecture makes a lot of sense. Resilience, performance, security, all tied to that separation of duties. Very cool. So with these components working together, how does Junos provide a logical way to group interfaces together and apply rules consistently?
That's where security zones come into play. Zones are basically logical groupings of network interfaces. Instead of writing rules for every single port, you group interfaces with similar security needs into a zone, like an untrust zone for the internet side, maybe a trust or internal zone for your LAN, perhaps a DMZ for servers people access from outside. And the really crucial rule here is An interface can only be in one security zone at a time. That enforces clear separation.
Okay, logical groups.
Right. And then your security policies, they're written between these zones. You define what traffic is allowed from untrust to DMZ or from internal to untrust and so on. This makes managing rules way simpler. Instead of potentially hundreds of rules, you might have just a dozen or so inter-zone policies. And maybe more importantly, it enforces segmentation. It makes it easier to apply least privilege, only allowing exactly what's needed between zones. If one zone gets compromised, that segmentation helps contain the damage.
That's a great analogy. Like departments in a secure building. Each department is a zone, and you have specific rules about who can go between which departments, not just locks on individual office doors. It brings order and control. It's not just for convenience, it's a core security concept for containment. Okay, we understand the architecture, zones help organize things, but how do we get really specific within those policies? What's the role of an application object in a security policy?
Good question. Application objects let you define traffic way more specifically than just protocols and ports. You can define things like, yes, protocol and port, but also specific application signatures like identifying actual HTTP traffic or SSH, or maybe even something like Facebook traffic. Policies then use these objects to match traffic. So instead of just saying allow TCP port 80, you can say allow application HTTP.
Why is that better?
Well, because applications don't always use standard ports, right? Or attackers might try to sneak stuff over a common port like 80. By matching on the application itself, the firewall can often do deeper inspection to make sure it really is HTTP traffic, for example. It gives you much finer control, it makes policies more accurate and robust against evasion techniques. Plus, it's clearer for audits you're explicitly allowing web browsing, not just port 800 and 443 traffic.
Right, so you can allow just HTTP, not potentially something else hiding on port 80. That's much more granular, more intelligent control.
Makes sense. Okay, but even with great architecture and policies, things sometimes go wrong. Troubleshooting is key. What if you think packets are getting dropped by the SRX and you need to figure out exactly why? Ooh, yeah, the classic troubleshooting scenario. For that, your best friend is often the Monitor Traffic Interface Detail command. This command basically lets you watch packets in detail as they flow through the SRX interfaces. It's like putting a probe right on the wire, but with added context from the device. You can see the packet headers, see how the SRX is processing it, and crucially, see if it gets dropped and often why maybe a policy denied it, maybe a screen blocked it, maybe routing failed. It's indispensable for debugging those tricky drop issues. I've spent, many hours staring at that output.
Sounds like a powerful diagnostic tool, almost like network forensics in real time.
Yeah.
Okay, and what if it's not a drop you suspect, but you just want a snapshot of all the connections that are working? See what's flowing through the box right now.
For that overview of active connections, you'd use Show Security Flow Session. This command gives you a list of all the currently active network sessions the SRX is handling. You get source and destination IPs and ports. You see any NAT translations that were applied, the protocols, how long the session has been active, and importantly, which security policy matched and allowed that session. It's probably one of the most frequently used commands on an SRX for troubleshooting. Instantly tells you who's talking to whom and how the firewall processed it. Great for confirming things are working as expected or spotting unexpected connections.
So these aren't just obscure commands, they're like the dashboard and diagnostic scanner for your network security engine. Essential tools for anyone managing these devices. Daily drivers, really. Okay, finally, let's loop back to a broader security feature. One that's critical today, going beyond just filtering or blocking patterns. Which Junos OS feature specifically targets things like malware, spyware, viruses?
That would be the antivirus feature, which is part of Junos OS's broader UTM capabilities, Unified Threat Management. Its job is exactly what it sounds like, scanning the actual traffic content for malicious code. Viruses, worms, trojans, spyware, ransomware payloads, all that nasty stuff. It's looking inside the data, not just at the headers or connection patterns like screens or basic firewall rules.
So it's inspecting the content itself?
Exactly. It usually uses a mix of signature-based detection, looking for known malware fingerprints, and sometimes heuristic analysis, looking for suspicious characteristics or behaviors in the code. It's a vital layer, because threats can sometimes be hidden inside seemingly legitimate traffic. So while screens stop floods and policies control access, antivirus targets the malicious payload itself. It's about defense in depth, catching threats at the network edge to complement endpoint security.
Right, not just blocking doors, but actually inspecting what's coming through them for hidden dangers. A kind of digital immune system for the network. Absolutely essential these days. And maybe a final thought for you, the listener, to ponder. In this world of constant cyber threats, getting a handle on these building blocks, screens, NAT, SPUs, zones, it's not just for passing an exam. It's really key to understanding the foundations that keep our digital world running, keep us connected, and hopefully keep us safe. It's about building that real understanding. Thank you so much for joining us on this deep dive into Juno's OS security fundamentals. Until next time, keep exploring, keep learning, and stay secure.